Good day, everyone. Welcome to our session for today. So, this time we are going to continue our discussion on the limit of a function. So, this is the part 4 of our lecture on the limit of function. So, just to see if you have already done the exercises, just for your preparation for your coming quiz in few days' time. Okay, so you practice this one. And today we are going to discuss about one-sided limits. So it is in this discussion that we are going to determine, or we can determine whether the limit of a function exists or not, or does not exist. Okay, so this is the basic concept that we are going to use for this topic on the limit of a function, specifically on one-sided limits. In the definition of limit of a function, there should be an open interval containing a such that f must be defined at every number in that interval except possibly at a. Okay? So given any real number a, we can find functions which are defined only to the right of a or only to the left of a. If the function f is one such function, then the limit does not exist. Alright? So, for example, so we have here an example of such function. We have f of x equal to square root of x, and the other one is g sub x equal to the square root of 4 minus x. Okay, so I will explain to you later why is that so. Now let's take this definition for one-sided limits. Let f be a function defined at every number in some open interval. Our open interval here is a and c. So what does it mean, open interval? So it means that if you have this number line, so we have here our a and we have our c. Okay, so values that belongs to this interval excluding a and c. So we can write this as a, c. So parenthesis class means excluding a and is excluding c, only values within this interval but excluding a and c. Okay, so this is what is meant by this open interval represented by this. So the limit of f of x as x approaches a from the right is L and is written in this expression. So limit f of x as x approaches to a from the right. So the positive here means that the values are from the right equal to L. Okay? So limit of a function as x approaches a from the right. So that is denoted by this symbol plus. So x approaches a from the right. So the limit is equal to L. Alright? If the values of f of x get closer and closer to L as the value of x get closer and closer to a, and when the values of x are greater than a. right? So these are the conditions. Okay. Example: if you are given this instruction to evaluate the following limits, and you're given, say, here, limit of the square root of x minus 3 as x approaches 3 from the right. So what is our L here? So what is this equal to? Okay, so it means our L here. What is our L? Okay, so if we are going to illustrate this in our number line system, so we have here our 0, 1, 2, we have 3, 4, we have 5. Okay, so our x approaches 3 from the right. So this is our 3. Alright, this is our 3. Then x approaches from the right. Alright. So what is the limit? So in our previous lesson, to determine the limit, we just do direct substitution of this value, and let's get the result. So this means that we have uh, as x approaches to 3 from the right, so we have square root of, we have x, which is 3, then minus 3, so we have the limit of the function is equal to 0, because 3 minus 3 equal to 0, square root of 0 equal to 0. So that is the limit. Okay, now for example number 2, so we're given the limit of the quantity square root of x squared minus 4 plus 5 as x approaches to 2 from the right. Okay, so the number line, we have here our 0, we have 1, we have 2, this is our 3, this is our 4, 5. Okay, so you can put as many numbers as you can, 6, and so on and so forth. Okay, so x approaches to 2, so this is the number that x is approaching, right? That is also from the right, okay. So when you evaluate the limit, so you just substitute. So we have when x equal to 2, so square root of 2 squared minus 4, then plus 5. Okay, so this one, 2 squared equal to 4 minus 4, 0. So square root of 0 is 0, then plus 5. So therefore, the limit of the function from the right equal to 5. Okay. Right, so this is an illustration class of a limit of a function, or one-sided limits. No limits from the values of x approaching to the values of a coming from the right. Okay. Next, we have if a function f, or let f be a function defined at every number in some open interval be a. Okay, so we have another open interval here, be a. So assuming these are b, these are a. Okay, so we consider values of x within this range. So b a. So it means that values between a and b, excluding b and a. Okay, so let f be a function defined at every number in some open interval be a. The limit of f of x as x approaches a from the left is L, written as, okay, limit of a function of x as x approaches to a from the left. Okay, so the symbol here, or the sign here, means from the left, equal to L. So the limit is equal to L. Alright, so we are using values from the left going to a, and a is the number that the value of x approaches to. If the values of f of x get closer and closer to L as the value of x get closer and closer to a, and when the values of x are less than a. Okay, so that's the condition. So for example, if you're asked to evaluate the following limits, so for example this one, so what is the L here? What is our L? Okay, so we're asked to solve for the limit. Okay, so using again the number line for our illustration, assuming this is our 0, so we have 1, 2, 3, 4, 5, we have 6 here. Okay, so the negative here says that from the left. Okay, so this is the number approached by x, that is 5, and that is coming from the left. So the negative there indicates left. Okay, so coming from the left towards that value 5. Okay, so what is the limit? Okay, so by direct substitution, we have square root of 5 minus square root of 5 minus x, where our x approaches 5. So 5 minus 5. So again, this is 5 minus 5 equal to 0. Square root of 0 is equal to 0. So this is the value of our L, the limit, for one-sided limit. Another example is this one. So limit of the quantity square root of 1 minus x squared plus 2 as x approaches to 1 from, again, this is from the left. Okay, so for our number line, this is our 0, we have our 1 here, our 2, our 3. Okay, so the number approaches 1. So this is our 1. Then from the left. Okay, so what's the answer here? What is our limit? So by direct substitution, so this is square root of 1 minus our x is 1, so 1 squared. And then we have plus 2. So the 2 here is outside the radical. Okay, so 1 minus 1 squared equal to 0 because 1 squared is 1. So 1 minus 1 is 0. So square root of 0 is 0 plus 2. So you have 2 here as RL as the limit. Okay, so I hope it's clear. And I hope that you understand this one because we will use this concept in our next related topic. Okay. So in some cases, a function may approach either of two different limits depending on whether the variable approaches its limit through values larger or smaller than that limit. So in such a case, the limit is not defined or does not exist, but the right hand and left hand limit exist. In some cases, functions may approach either of the two different limits depending on whether the variable approaches its limit through values larger or smaller than that limit. So in such a case, the limit is not defined or does not exist, but the right hand and left hand limit or limits exists. So for example, if you're given this illustration, so you see here that we have this value approached by x, so we can define the limit of the function. Okay, so we have here x approaches c. Okay, so x approaches c. From the left, we have here from the left. So we have negative. And we also have, now we are considering this part here of the graph. Okay, so we're considering this. So we just cover the other graph, just focus on this. So we're approaching C here. And we also have coming from the right towards C. Okay, so in this case, we are going to consider this part. Alright? Now, considering this part here, as x approaches to C, so what is the limit? So we see that the limit is, so from here, we have the limit, looking at the picture, so the limit of f of x as x approaches to C, okay, x approaches to C, that is from the left. So from our illustration, we can see that this is equal to 3. Okay, so the limit exists and that is equal to 3. Now, considering this other part, we have the limit of f of x as x approaches to C, but this time it's coming from the right, so we have positive. Okay, so positive meaning coming from the right. So what is the value? So if you look at this picture here, so coming from the right, we have this picture. Okay, so what is the limit? So the limit is this one. Okay, so the limit is equal to 5. Alright, so both limit exist. So here, coming from the limit of f of x as x approaches to C, coming from the left, so equal to 3, right? So this value here, so considering this graph, and limit of a function of x as x approaches to c coming from the right. So we are considering this graph, and that is equal to 5. So both exist but they are not equal. Okay, so this is what we call the limit limit from the function, or limit of a function, or left hand limit, left hand limit. We can call it LHL, left hand limit, LHL. Okay, and we can call the other one as right hand limit. Okay, right hand limit, or RHL. So for the first one, it means that coming from coming from left, which is indicated by this negative here. So left hand limit. The other one is right hand limit, right indicated by this positive sign. Okay, so in this case, as mentioned in this statement here, in some cases a function may approach either of two different limits. So these are the two different limits, 3 and 5, depending on whether the variable approaches its limit through values larger or smaller than that limit. So in such a case, the limit is not defined or does not exist. So in this case, we can say that the limit of the function does not exist because the left hand limit is not equal to the right hand limit. So this is, or the limit of the function does not exist. Alright, so it does not exist, or DNA. Okay, so I hope you understand this one. Next, we have, if the left hand limit and the right hand limit both exist and are both equal, and that is equal to L, then the two-sided limit expressed by this notation, limit of f of x as x approaches to a, exists and equal to L. So this expression here, if this condition satisfied, then this exists and that is equivalent to L. Okay, as mentioned here. If the left hand limit and the right hand limit both exist but are not equal, the left hand limit, so take note on this, if the left hand limit and the right hand limit, both of them exist but are not equal. Okay, so take note on this, are not equal even though they both exist. So it means that, or another possibility is that if one of these exists, meaning either the left hand limit exists or the right hand limit exists, the other one does not exist, then the two-sided limit does not exist. Alright, so when we speak of two-sided limit class, if you can see that there is no sign plus or negative above a, so that indicates a two-sided limit. Alright, two-sided limit. Okay, so in this case, if this condition above is not satisfied, okay, so the first condition, if this is not satisfied, then the limit does not exist. But if this is satisfied, then the limit exists. But if the scenario is something like this here, on this part, okay, if the scenario is like this part here, this statement, then the limit does not exist. Okay, so this one, it means exist. So the two-sided limit exists if this is satisfied. But for this condition, if it falls into this scenario, then the limit of the function does not exist, or we call it DNA. Okay, so I hope this is clear. Next, for example, if you're given f of x equal to square root of x squared minus 25, and you are asked to determine if the limit of f of x as x approaches to 5 and limit of f of x as x approaches to negative 5 exists. So notice here that there is no sign above 5. There is no positive or negative. So it means this is a two-sided limit. Okay, here above the 5 there is no sign of negative or positive also. So it's a two-sided limit. So what we're going to do is to prove that or to determine that this function given by this expression above exists or does not exist. So the condition is that we have to determine first the one-sided limit, left hand limit and right hand limit, and then we compare. And if they're both exist and are equal, then the limit of the function exists. Otherwise, it does not exist. Okay, so for the first part, we have the limit of f of x as x approaches to 5 from the left. Okay, so we have here a negative equal to. Okay, so what are the values that is coming from the left? Okay, so the best way is to draw a. Okay, so assuming this is our number line. Okay, so you'll just take this line. Okay, so assuming these are 0, these are 1, 2, 3, 4, 5, 6, 7, 8. So here on the other side we have, okay, later we'll do it later. So for this first part, the left hand limit, so this is the number that x approaches to. Alright, so negative here means from the left, so values from the left going to the right. Okay, so let us determine if the limit exists, no, from. Okay, so substituting, we have okay, so if you have this is equal to square root of x squared minus 25. Okay, so substituting the values of x when x equal to 5, so this would be so this is 25, so 5 squared Alright, so we have 5 squared is 25 minus 25 equal to 0. Square root of 0, that is also equal to 0. Okay, so the limit is equal to 0. Now if we evaluate the limit of the function of x as x approaches to 5, but this time coming from the right. Okay, so from the right. So let's check. So again, this is square root of, so x squared minus 25. So our value is coming from the right. Okay, so from the right going to this direction. So this is this also 5 squared minus 25, where 5 squared is equal to 25. So 25 minus 25, 0, square root of 0, that is also 0. So I think, can you imagine what equation is this? What kind of equation is this? This is what do you think? A half? If you don't know what kind of function is this, then the best way to do is to graph, to graph the function, so that you can see the what is really the. Okay, so let's try to graph this function. Parang it's clear class. So you have x and f of x, but if you know, no, from the standard formula, then you will be able to determine what kind of function is this. But if you don't know, then you just graph. Okay, so tabulate first the value. So if you have, so for example, if you have x equal to, if x equal to, say, okay, so you know what values that are not allowed here. So remember from our previous discussion, we have a square root of something, and this time our something is x squared minus 25. Alright, so the condition here is that the radicand is the terms under the radical sign, so this should not be negative. It means that it should be greater than or equal to 0. So from here you can solve for our x, right? So subtracting both sides by 25, so you have x squared equal to 25. Then taking square root on both sides, so you have x equal to plus and minus 5. Okay, so square root of 25 is 5. So when you're taking square root both sides, or yes, so you have two values for x. So for example, if x equal to, say, minus, we'll start with say So we're not allowed 4 here, because if you have, say, 4, let's start with 5. When x equal to 5, so what will happen? When x equal to 5, so this is 0, or f of x is equal to 0. When x equal to, say, 4, minus 4, so in minus 4, what will happen? So 16 minus 5, so this is undefined. Okay, so undefined. We put it u. We cannot determine the value. When x equal to minus 3, okay, so minus 3, so square of minus 3, 9, minus 25, that is also undefined. When 2, so when this is 2, it is also undefined. And this is 1, negative 1, so negative 1 squared, 1 minus 25, square root of 24, negative, so that is also undefined. Okay, so when this is 0, so that will be square root of minus 25, so that is also undefined. Alright, if you have 1, so let's continue it here. Sorry for the sideways class. I just want you to understand it well. Okay, so this is our x, this is our f of x. Okay, so let's continue. When x equal to, say, 1, so that's still undefined, right? So when x equal to 2, this is still undefined. When 3, this is undefined. When 4, this is also undefined, right? This is still undefined. When 5, we have 5, this is 0. When 6, so let's try 6. So when this is 6, so 636 minus 25. What is 36 minus 25? So 36 minus 25, so that is 11. So square root of 11, so this is square root of 11, so that is 3 point something. So square root of 11, that is 3.3. Okay, so 3.3. Okay, so if you graph this class, if you graph this, so when x equal to okay, so that's not okay, I think we have to draw somewhere else. So assuming this is a 1, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, so negative 1, positive 1, positive 2, positive 3, positive 4, positive 5, and we have 1, 2, 3, 4, 5. So this is our f of x. x. Okay, so when x equal to -5, so here 1, 2, 3, 4, 5, so -5, our f of x is, see, 1, 2, 3, 4, 5, so this is +5. Okay, so when x equal to -5, we have our f of x equal to 0, so it's somewhere here. When x equal to +5, we have our x is somewhere here, f of x. Okay, so 0. So if we try 6, if we try x equal to 6, so what happens? This would be 3.3. So if that is +6, we have 3.3. So if this 1, 2, 3, so it's somewhere here. Sorry. When 6, so somewhere here. This is 6. So we have 3 point something, no? So it's somewhere here. And that the same class if you assume value for -6. If you take -6 here, it's the same. No? If x is -6, so assuming x is -6, so that gives you also 3.3 for f of x, because when you square negative, so that is positive. So positive 36, right? -25, that is square root of 11, and that's 3.3. So if negative siya, if -6, so it's also somewhere here, right? Okay, it's somewhere here. If this is our 3, or if you have, if this is okay, so for example, if this is 7, so 749. Okay, for when x equal to 7, or positive or -7, so 49, so that becomes 49 minus 25. So 49 minus 25, that is 24. So square root of 24. So what is the square root of 24? That is 4.8. Okay, so as you extend this one class, okay, so if this is 7 here, this becomes 4 point something, no? 4 point, this is 4, so 4.8, almost 5. So it's almost 5, so it's somewhere here, or say something here. Okay, so initially we have this graph, so it will just reflect on the other side. This is symmetric. Sorry, this one. So if you connect this, so we have this graph, and we have this graph. Okay, so now here for this, as x approaches from the left of the +5, so from the left to +5, okay, and if x approaches to 5 from the right, so you see that the value of f of x as x approaches to 5, that is equal to 0. Okay, so you have here 0, and you also have here 0. So both limit, the left hand limit and the right hand limit exist, and that is equal to 0, and they are both equal. So therefore the limit of f of x, or the limit of f of x, or the two-sided limit, and the limit of f of x as x approaches to 5, that is also equal to 0, and the limit exists. Okay, so the limit does exist. Alright, so that is for first part. Now we have here limit of f of x as x approaches to positive 5. How about this one? Limit of f of x as x approaches to negative 5. Okay, so this is the limit, the value that is approached by x. Okay, so we will do the same. So we have limit of f of x as x approaches to, so this time x approaches to negative 5. Okay, negative 5. Okay, so this is the two-sided limit, which is equal to square root of x squared minus 25. Alright, so here as x approaches to positive or negative 5 from the left. Okay, so we have here from the left. Okay, so coming from the left towards that negative 5. Okay, so this is equal to, so we just substitute the value of x. So we have minus 5. Okay, minus 5, when you square this one, that is also positive 25. So this will be 25 minus 25. So square root of 25 minus 5 is equal to 0. So square root of 0, that is equal to 0. So this is 0. Okay, so the other one, limit of f of x as x approaches to negative 5 from the right. So our x here approaches to minus 5 from the right. Okay, so we have plus here from the right. So again, this is equal to the square root of, so this time approaches from the right. Alright, so again, minus 5, squaring this one. So square of minus 25, minus 5 is 25, positive 25. So positive 25 minus positive 25, so that is equal to 0. So square root of 0 is equal to 0. Okay, so we see here that both limit exist and equal to 0. Alright, so both limit exist and both equal to 0. So therefore, the limit of f of x, in this case, the limit of f of x, two-sided limit, as x approaches to negative 5, also exists, and that is equal to 0. Okay, so in this example, we're able to determine the limit of f of x as x approaches to 5 and the limit of f of x as x approaches to negative 5 both exist. Okay, so hope this is clear to your class. So if you understand this one, then there's no problem that you cannot solve the next example. So the basic concept is already explained here. Okay, so in our next example, so this is our first example. That was our second example. First example. Okay, now for the second example class, so we have it here. So we're given f of x, x minus 1 if x is less than or equal to 3, and the function f of x is x squared minus 7 if x is greater than 3. So the same thing, you need to tabulate values and then try to graph so that you can see, okay, you can see what's really the behavior of the graph. Alright, so here we have a table for x less than or equal to 3. So assuming this is our number line, okay, so we have, say, 0, we have 1, 2, we have 3, we have 4 here, 5, and so on and so forth. Okay, so let's try here, say, negative 1, negative 2, negative 3. Okay, so you can try as many numbers you want. And you have negative 4 and so on and so forth. Okay, so we have here the interval x less than or equal to 3. So this is our 3 here. Okay, so it means the values belongs to this. So this is our x less than or equal to 3. Okay, and then the other interval is x greater than 3. So you have on this part here, so this is our x, values of x that are greater than 3. Okay, now if you graph this function, so we have here the condition that for this interval here, for this interval, you need to use the function f of x equal to x minus 1. So in other words, if you say take value minus 3, so f of x equal to x minus 1, so you have to use this. So when x equal to minus 3, you substitute it here. Minus 3 minus 1 equal to minus 4. Alright, when x equal to minus 2, so substitute it here. Minus 2 minus 1 minus 3. When x equal to minus 1, so minus 1 minus 1 equals minus 2. When x equal to 0, so when this is 0, so 0 minus 1 equal to minus 1. When x equal to 1, okay, so when x equal to 1, so 1 minus 1, we have 0. When x equal to 2, so when this is 2, so 2 minus 1 equals 1. When x equal to 3, so 3 minus 1, we have equal to 2. Okay, so that is considering the left hand, on the left part, the left part of 3, the left hand limit, or the left hand interval. Now if you consider the right hand interval, so we also have to begin with 3. Okay, so sorry, this is a very small, written very small. Okay, so when x equal to 3, okay, so because we have here x equal to x is greater than 3, but still we have to use 3 because the interval here is we have 3, so the interval here is 3 to positive infinity, right? This is positive infinity. Okay, so that is the interval on the right side. Okay, so a parenthesis meaning excluding 3, but here on the other side we have negative infinity, right? And we have 3 less than or equal to 3, so it means you can uh, consider or include 3. Alright, so we're done with this side here, the left side. So now we'll go to the right side. So 3 and positive, this is the open interval, 3 and positive infinity. So we can consider 3 also when x equal to 3, but this time we have to look at this. Okay, sorry I put it here, but I should put it here. So when x equal to 3, so I will rewrite this. When x equal to 3, okay, let me change the color. So when x equal to 3, so we have f of x equal to 2. Okay, so this is 3, so 3 squared, 9, 9 minus 7, that is 2. Okay, when x equal to 4, so now we're going for numbers greater than 3. So when x equal to 4, so we have 4 squared, 16 minus 7, we have 9. When x equal to 5, so 5 squared, 25 minus 7, so we have 18. When x equal to 6, 6 squared, 36 minus 7, so that is 36 minus 7, that is 29. When x equal to 7, that is 49 minus 7, so that is 42. When x equal to 8, 8 squared, 64 minus 7, that is 50. So 8 raised to the power 2, that is 64 minus 7, that is 57. And when x equal to 9, 9 squared, 81 minus 7, 74. When x equal to 10, so 10 squared, 100 minus 7, we have 93. So now if you are going to plot the points, alright, so you will see this graph. So here, when x equal to minus 3, so when x equal to minus 3, so we make it 10, 20, 30, 40, because number is already here's number. So we have here minus 10, minus 20, and so on and so forth. So that's why when x equal to minus 3, you have f of x equal to minus 4. So if this is minus 10, so half of it is 5. So we have minus 4, so more or less here at this point. Okay. Then when x equal to minus 1, sorry, minus 2, so minus 2, so minus 3, so it's here. When x equal to minus 1, so minus 2. Okay, so very close to the x-axis. When x equal to 0, negative 1. Okay, so very close to 0 also here. And when x equal to okay, so when x equal to 1, f of x is 0. Okay, so here. So when x equal to, sorry. So when x equal to 2, when x equal to 2, so we have f of x equal to 1. Okay, it should be somewhere here. And when x equal to 3, f of x equal to 2, so it's somewhere here. And when x equal to 4, right, so when x equal to 4, we have 9, so it's somewhere here. When x equal to 5, f of x is 18, so 5 is 18, so this is 20, so more or less here. Okay, so when x equal to 6, so we have 29. So if this is 30, so it's somewhere here. When x equal to 7, okay, so when x equal to 7, 42 ang f of x. So 7, so we have 42. So 42, so a little bit higher. So it's somewhere here. So when x equal to 8, that is 57. So 8, so 57. This is 60, 70, so 57, so somewhere here. So when x equal to 9, then we have f of x 74. So 9, so this is 70, this is 80, so 74, so below 75, so it's somewhere here. And when x equal to 10, so f of x equal to 93. So 10, 93, this is 90, 100, so 93 is somewhere here. So more or less this one. Okay. Now if you are going to connect, connecting the points, so as you can see from the illustration, so connecting the points, so you will have this. You can extend, no? So it means you can have more values for x going to the or from the left. So that's why you put an arrow here. Similarly here, you can also put an arrow to indicate that you can also extend the values. Okay, so connecting the points, so you'll have this graph. Okay, right, so that's why we have here, we have to determine if the limit of a function exists. So what we did was first we tabulate and then we graph. Okay, so we tabulate and then we graph, and after that we have to so we have to determine whether the function, the two-sided function exists or not. So first we need to solve for the limit of the function as x approaches to 3, that is from, okay, so I will enlarge this. Okay, so from x, limit of function as x approaches to 3 from the left side, so this is negative. Alright, okay, let me expand further. Okay, so we have here x, so substituting, so we have x minus 1 now from our, so x minus 1 from the left, x approaches to 3. Okay, so where is 3? So this is our 3 here. Okay, so this is our 3. Alright, this is our 3. So x approaches from the left. Okay, so from the left. Okay, so consider this graph, the blue one. Okay, so our values approaching from the left towards 3. So substituting the value from this equation, so it means that we are on this interval. Alright, so we are in this interval, so we have to use this x minus 1. So x f of x equal to x minus 1. So substituting, so substitute the value of x, which is 3. So 3 minus 1 equal to 2. Okay. Now, x, for x approaching or approaches 3 from the right. Okay, so from the right, so we use another interval, right? So for this interval, we have this condition. Now for x greater than 3, so we have to use this, right? So we have to use this. Okay, so limit of f of x as x approaches to 3 from the positive. So we have to use this equation or expression x squared minus 7. Alright, so substituting. Okay, so substituting, we have x, so we have x, which is 3, so 3 squared minus 7, so we have 3 squared 9, 9 minus 7 equal to 2. Okay, so we see that the limit of the function, the left hand, no, the left hand limit, so we can see here that the left hand limit, is equal to 2, alright, and it exists, and our right hand limit, our right hand limit also exists, and that is also equivalent to 2. So since the left hand limit and the right hand limit both exists and are equal to 2, so therefore we can say that the limit, we can say that the limit of the function, or limit of the function, the two-sided limit of the function f of x as x approaches to 3 does exist and is equal to 2. Okay, so I hope you understand this class, and there's another problem here related to this one. I want you to try it. Okay, so again, you just do the same. You have to tabulate, and after tabulating the values, you plot the points, and then after plotting the points, you connect the points, and then start the try to start finding out whether the limit exists. And to find out that the limit exists, we have to compare the left hand limit, meaning left hand limit and right hand limit. Now, if the sign is negative above the values that x approaches to, it's negative, meaning that is the left hand limit, and if that is positive, that is the right hand limit. Then you compare the two values. If both limit exist and they are equal, then we can say that the limit of the function exists, and you just determine what that value is. So that is the limit. Okay, so that's all for today, and once again, thank you very much, and hope to see you again in our next part 5 of our discussion on the limit of a function. Have a good day and stay safe and healthy always. God bless everyone. Bye bye.